Consider the uncovered interest parity equation in exact form given as. So consider the uncovered interest parity equation, which in exact form is given to us as 1 plus IT is equal to 1 plus I star T. And here remember IT is the domestic interest rate, I star T is the foreign interest rate, ET is your nominal exchange rate, number of units of foreign currency per 1 unit of domestic currency, ET plus 1 is your expected future exchange rate. So this is uncovered interest parity equation in exact form, and we want to show how it implies this approximation. For this, what we're going to do is, firstly, we're going to take natural log on both sides of the equation. So take natural log ln on both sides of the equation, right? So that's what we're going to do first. We're going to take natural log on both sides. So this becomes ln 1 plus it. And here, when we're going to apply, we're going to take natural log over here also, which is going to be natural log of 1 plus I star t into et divided by et plus 1. Now we're going to use the log on the right hand side. We're going to use a natural log property, which says that if we recall, now this is now here we're going to if we're finding the natural log of a product, we can write it as the sum of the natural logs, right? This is a property of logs. So ln AB is just ln A plus ln B. So we're using a property of natural logs here. So based on that, I can write this as ln 1 plus I star t plus ln et by t plus 1. Now the next thing I want to do is, now notice in the approximation we have a minus over here. I want to somehow bring a minus here. So for that, what I'm going to do is I am going to rewrite this term ln 1 plus I star t. So what I'm going to do is we're going to rewrite this term. Instead of et plus 1, we can write this as so I can take the reciprocal of it, right? I can rewrite this term et minus 1, right? We basically have a minus in this approximation. We need to bring the minus from somewhere. For this, I'll rewrite et by et plus 1 as just et plus 1 by et power minus 1. Why am I doing this? Because now we can use the log, now we can use the property that ln a power b is just b ln a, right? So if you're taking the natural log of a power b, you can just take the power as a coefficient of log. So this allows us to bring a minus sign over here, right? Because we can take it over here. So now if I rewrite this is going to be ln 1 plus it is equal to ln 1 plus I star t. Using this property, we can write this as minus ln e plus 1 by et, right? So using this property, this minus has come out as the minus, which is on the power of et plus 1 by et, can come out as the coefficient of ln, right? So this is how we bring in the minus here, because this, so the first step was you take natural log on both sides, then you use the fact that ln ab is ln a plus ln b. Then I just rewrite this. Instead of writing et by et plus 1, I can write it as et plus 1 by et power minus 1, right? You just we can write it like this instead. And the reason we wrote it like this was so that we can take this minus 1 as a coefficient of ln, and we can get a minus sign that we saw in the approximation, right? So now, further, what we're going to do is, we will now, in order to further proceed, we'll now use the approximation. So now to proceed further, we'll have to use the approximation, because see, remember we're saying, okay, form the exact form we want to find an approximation. Now we have read it in the exact form in this way. Now we'll apply an approximation. So here we'll use two ideas. That one, that ln 1 plus x is approximately x for small values of x. And by small values of x, here we mean values close to 0. So this approximation holds in general for small values of x close to 0. So for small values to x, so we're going to use this approximation which applies for small values of x. And now we can notice where we're going to apply this. We're going to apply it here. ln1 plus it would approximately be it for small values of it. ln1 plus I star t would approximately be I star t for small values of I star t. This is becoming closer and closer to this, right? When instead of ln1 plus it, we'll write it. Instead of ln1 plus I star t, we'll write I star t. We still need an approximation for this. Right, you still need an approximation for this, right? So for this approximation is applying to 1 and 2, right? But these are in the form ln 1 plus x, here x is it, here x is I star t. Right, so now what we're gonna do is so we're gonna use another approximation for the third term that's left, where we're gonna use the fact that ln xt plus 1 by xt is approximately xt plus 1 minus xt by xt. So ln xt plus 1 by xt is approximately the growth rate of x in year t, right? So this is approximately growth rate of x in year t, right? So this is approximating the growth rate of x in year t, and this is for small values of the growth rate, right? For small values of xt plus 1 minus xt by xt. Right, so for small values. So basically, for small values of the growth rate, we can approximate the growth rate as ln xt plus 1 by xt. Right? Now, actually, if you want to look at this, if you notice, the second approximation actually comes from the first. This is just FYI. FYI, the second approximation, this is just for information, that the second approximation actually follows from the first, right? The second approximation actually follows from the first. It's not something new, it's just an implication of the first approximation. Just from the first. Right? Because see what happens is if I have the growth rate of x in year t, it's xt plus 1 minus xt by xt. So we know okay, this is approximately ln 1 plus xt plus 1 using the first approximation. Because here x is just, because here the term that we're taking as x is just this, right? This is just like x in this case. And we know this holds true for small values of xt plus 1 minus xt by xt. Right? It's approximately this. And then if you simplify this, this just simply becomes ln xt plus 1 by xt. So the fact that you can approximate your growth rate using, and this is we know for small values of x, because we know ln 1 plus x will approximate x for small values of x. And here x is just xt plus 1 minus xt by xt. Right, so this is just FYI. Now the second approximation actually follows from the first. So here to go to derive our from our exact form, the approximated version, we take natural log on both sides, do a bit of manipulation, and then the approximations that we'll use are essentially ln 1 plus x is approximately x for small values of x. This allows us to write ln 1 plus it approximately as it, ln 1 plus I star t is approximately as I star t for small values of it and I star t respectively. And then we're going to use the fact that the growth rate of any variable can be approximated using logs as well, where xt plus 1 minus xt by xt, which is the growth rate of x in EAT, can be approximated as ln xt plus 1 by xt. So here ln EAT plus 1 by ET is approximated by, is approximately the same as the growth rate of the exchange rate in year t, right? So it's ET plus 1 by minus ET divided by ET, right? So we're going to use these approximations, that we're going to use the fact that ln 1 plus x is approximately x, and we're going to use the fact, right? So here we're basically using two approximations, one that ln 1 plus x is approximately x over here, and that this ln ET plus 1 by ET is approximately equal to the growth rate of the exchange rate in EAT. Right, so using these two approximations, what we can do is we can write so we know we're here using the fact that ln 1 plus x is approximately x for small values of x, so ln 1 plus it is approximately it for small values of it, and ln 1 plus I star t is approximately I star t for small values of I star t. And then we know for small values of et plus 1 minus et by et, this ln et plus 1 by et is approximately the same as the growth rate of mean et. Right, so it's minus EET plus 1 minus ET divided by ET. Right, so we have shown that this is how this exact UIP implies this approximated version. Remember, this approximated version holds. So this is basically for small values. So for small values of I starting ET plus 1. So just note over here, note when the values of the interest rate, so over here we just want to note when the values of the interest rates, IT and I starting, when the values of the interest rates and the expected appreciate and the expected rate of appreciation rate of appreciation are small enough, here we mean close to 0. And by small enough, so here also when we said for small values, we meant close to 0. Right, so if I just go back a bit, here we also said this holds true for small values of this. So what we mean over here is close to 0. When we're talking about small values here, these approximations hold for small values. So we mean close to 0, right? Are small enough, close to 0 in decimal form. Close to 0, because we know IT and I start will be percentages, so close to 0 we mean decimal form. This version of the interest parity is a good, this version of the interest parity, so this version, interest parity is a good approximation into the exact version. Right, so this is how we learn. From the exact version of UIP, we can go to the approximated form. The whole idea is you just take natural log on both sides, do a bit of manipulation, and then just apply the approximations that ln 1 plus x is approximately x for small values of x, which allows us to write ln 1 plus it is approximately it for small values of it, and ln 1 plus I star t, we can write it as approximately as I star t for small values of I star t. And then we have that we can write, and then we'll use the fact that ln xt plus 1 by xt is approximately the growth rate of x and et for small values of the growth rate. So this allows us to write this as et plus 1 minus et by et.